UNisOn is a multiplayer, mind-controlled card game based on the popular card game of Uno. This mind control component allows individuals with communication and motor deficits to uniquely engage in gameplay with others. We record EEG signals from the sensory motor cortex of the brain, and then we analyze and interpret these signals to understand the player's intended move without them actually having to move their body or speak. This is what allows us to generate this virtually mind-controlled experience. McGill Neurotech split into 3 sub-teams in order to achieve this. We have the data collection team, the signal processing and machine learning team, and the software team.
The method of data collection our team uses is EEG. EEG, or electroencephalography, is a non-invasive method of collecting electrical signals from the brain. For UNisOn, we decided to use motor imagery and jaw clenches to control and play the game. The motor imagery signals are used to shuffle through the user's hand of cards, left and right, and the jaw clench is used to select the cards the user wishes to play. To ensure a positive user experience, we needed to collect data from various participants to find the best way of identifying these signals. We collected data ourselves from various male and female subjects in their early 20s. To gather the data, we positioned 4 electrodes directly above the sensory motor cortex, specifically at placements C1, C2, C3, and C4, following the standardized 1020 system for electrode placement. Our setup used the OpenBCI 8-channel biosensing EEG board along with passive wet electrodes. Once the electrodes were properly set up, we recorded EEG data from participants using a data collection platform developed by our software team. Each participant followed a sequence of tasks, alternating between imagining moving their left arm, their right arm, and clenching their jaw for 10 seconds each, and resting for 20 seconds, repeating the cycle for a total duration of 5 minutes per trial. After collecting this data, we sent it off to our signal processing and machine learning team.
A very common and highly effective way of classifying left-right motor imagery data is to use common spatial patterns, or CSPs. The idea is to find linear filters that maximize the difference in variance between signals belonging to different classes. After applying the signals, they can be averaged to obtain feature vectors that can then be fed into any classifier. For pre-processing, we first apply a notch filter at 60 Hz to remove power line noise. We then apply a series of bandpass filters to obtain 9 power bands that go from 4 Hz to 40 Hz, to the C3 and C4 channels to obtain 18 time series. These signals are then normalized before applying the CSP algorithm and averaging out the signals to obtain a feature vector that is finally fed through a support vector machine for classification. We also explore deep learning techniques to improve classification results using EEGNet, a highly successful CNN that uses depth-wise and separable convolutions to limit parameter count. In our first approach, we fed normalized and filtered signals to EEGNet, which gave better results than what we obtained with SVMs and CSPs. We then wondered if it was possible to combine the 2 methods. In our final approach, we first applied the 9 bandpass filters to separate the signals into different power bands. We then feed the filtered signals to EEGNet, but this time we replaced the input convolution with linear filters similar to what is used in CSPs. This method concurrently optimizes the filters and the classifiers using gradient descent and preserves some temporal information.
In this project, we built an innovative user interface that seamlessly integrates live data with interactive gameplay. First, live data is read into a signal processing listener. This backend component is responsible for capturing real-time signals from the brain-computer interface, or BCI. From the SIGI listener, the data is sent to a main server via ZRMQ. This server is the brain of our operation, managing all game state logic. One of the key functions of the server is to manage the player's hands of cards. Here's how it works. When a game starts, the server assigns each player a unique identifier and deals them an initial hand of cards. This information is tracked and updated in real time. As players make moves, the server updates the game state. For example, when a player plays a card, the server receives this action, updates the game state, and then communicates the new state to the front end through WebSockets. Our front end is composed of a home screen and a game board. Within our game board, players can see the center card pile, the hand of cards. The UI visualizes changes in real time, using WebSockets to communicate and receive info from the server. Players can see cards being played and their card friends shifting left or right, all based on motor imagery signals read to the server. The server's logic ensures that each player receives the correct hand of cards and that the game state is consistently updated. For example, if player 1 plays a card, the server updates player 2's view to show the new card played. It also sends signals to start or end the game, and it handles the real-time direction signals from the BCI. With this setup, we've created a dynamic and engaging user experience that bridges the gap between neuroscience and interactive gameplay. Our UI not only harnesses the power of BCI, but brings it to the stage of multiplayer gaming, stimulating engagement, collaboration, and cognitive enrichment.
We wanted to create a project that would support individuals with complex medical conditions such as ALS, Parkinson's, and forms of paralysis that interfere with the individual's ability to communicate. These individuals often experience increased feelings of loneliness and isolation, which are known to pose numerous health risks and are central to well-being and cognition. Now, interestingly, research has found gameplay to reduce depression as well as promote memory. This is extremely important as in individuals that have suffered spinal cord injury, research has identified high rates of depression as well as a higher risk of cognitive impairment. UNisOn effectively reduces these barriers and allows these individuals to reconnect with those around them.
If you're interested in trying out UNisOn, you can find all the necessary code on our GitHub page, Begil Neurotech, under the 2024 repository. On the README page, we've provided a link to a Google document that details the steps for setting up the UI.